Well, first, there's an announcement. There will be no class next week. Due to a PhD exam which I have to organize. No, this is not it. So the plan is to have an extra meeting at some point in the future. But next week there won't be anything. I'll have to be at my computer organizing an exam for PhD students. Well, let's briefly recall what we did last week. We did discuss singular chains and singular homology, in particular relative homology. And we did talk about the excision property. We'll shortly see an application, but before we do that, let's recall what the what the excision property actually is. Suppose we have a subspace A of a space X, and we also assume that the closure of B is contained in the interior of A. Then we have isomorphisms which are induced by the inclusion of pairs. Let's see why this condition is important. Without this condition, the isomorphism may or may not be there. Well, example. Basically, we could take X to be more or less anything. Well, let's take, for example, X equal to sphere. and let's take both A and B to be a hemisphere. Well, let's see if this formula is valid. First let's look at the right hand side, and x comma a the result is isomorphic to the homology of Sn mod a point. We can take Pt to be any point inside A, and we have this isomorphism by the 5 lemma. Does this make any sense? Понятно ли, откуда берется изоморфизм? Значит, лемма о 5 гомоморфизмах. Встречалось ли такое? Okay, does anyone know what the 5 lemma says? The answer is no. Well, let's let me state a particular case of the 5 lemma, which is the case people normally use. 3, 4, and 5. Well, suppose I have a diagram. Where AIs and BIs are just abelian groups, and we assume that the rows are exact and all squares commute. If all arrows, except possibly the one in the middle, are isomorphisms, then so is the middle one. Corollary. Suppose we have a map of topological pairs, which basically means a map from a space, a continuous map from x1 to another space x2, which takes a subspace A1 to a subspace A2. And suppose this map is an isomorphism on the level of the ambient spaces, meaning the map from on the level of the homology of the ambient spaces, meaning the map from the homology of x1 to the homology of x2 is an isomorphism. And suppose the same is true for A1 and A2. Then the same is true for the relative homology. Does this make any sense? Так, значит, понятно ли вообще, о чем речь? Там всякие гомологии, там отображения, имеет ли это хоть малейший смысл? Окей.
Я, например, не часть связана с упражнением.
Так, значит, нижняя часть какой доски?
Ну вот то, что мы последнее писали.
Так, значит, связано значит, посредством слова corollary, что означает следствие. Значит, я утверждаю, что значит, вот 5 лемма влечет вот это следствие. Давайте подумаем, значит, понятно ли, какое имеет отношение 5 лемма к вот этому следствию? Is it clear what the 5 lemma has to do with the corollary? Нет, непонятно. Вот давайте, on the other hand, so some people say it is clear, and some people say it isn't clear. Okay, so who thinks it is clear? Wei, can you explain, what's your name? Can you explain to Semyon how this is related to this?
Should I write something?
Yes. Let's get rid of this.
By the construction of another theory that you let's be safe. So you get this picture sequence. That we should ignore is the classical minors and here should be 1 and 1. And also here everything should be with 2. So what errors do you have? You have this isomorphism and this 4 isomorphism by assumption and also this map. And by the 5 lemma, this is again an isomorphism. So that's it.
Semyon, did you understand the argument? Okay. Does everyone understand what's going on? Well, thank you. Wei, let's return to this example. Does everyone understand why we have this this isomorphism? This is isomorphic to this. Well, simply because the point has the same homology as the disk dn. Well, let's look at the left-hand side. Well, what happens? What happens when I subtract a closed ball from the sphere? Well, basically, I get an open disk. If I take the sphere, subtract a closed disk, I get an open disk, or which is the same, Rn. And the result I get is simply the homology of Rn. Oh, sorry, it doesn't need to be n. So the homology of Rn is not the same as the reduced homology of Sn. Why? Well, for example, in degree 0, if n is greater than 0, then in degree 0 here we have z, and here we have nothing, 0. And similarly in degree n, we have something here, but nothing here. This was a non-example. The purpose was to show that we cannot excise arbitrary sets. We need to check this condition. The closure of B is contained in the interior of A. Otherwise, problems may and often will occur. On the other hand, let's consider an example. This was a non-example. Now let's do an example. Let's prove that Rn and Rm, the Euclidean spaces, are not homeomorphic unless m is equal n. Those two spaces are we'll see two proofs, and the second one will generalize to arbitrary manifolds. Okay, but first of all, we know that Rn, both of them, are homotopy equivalent to a point. No surprises there. But how to prove that these spaces are not homeomorphic? Значит, Rm, Rn, n не равно m. Значит, что мы хотим? Хотим доказать, что они не гомеоморфны, хотя довольно-таки очевидно, что они гомотопически эквивалентны. Что делать? На первом курсе в топологии была какая-то очень похожая задача. Значит, вот у кого была на первом курсе топология?
Там надо точку выкинуть.
Во. Well, the first method which works for Euclidean spaces. So first method. If we have a homeomorphism from Rn to Rm, then we also have a homeomorphism from Rn minus a point to Rm minus a point. Rn minus a point is a homotype equivalent, not a homeomorphic, homotype equivalent to Sn Sn minus 1. And we know already that Sn minus 1 is not homotype equivalent to Sm minus 1 if m is different from n. But let's generalize this. Let's prove that if m and m are two topological manifolds, of different dimensions, then then m and n are not homeomorphic, although they might happen to be homotype equivalent. What do we do? This time, if we subtract a point, we get something, but the something may be complicated. Что делать? Мы хотим доказать, что многообразие разных размерностей не гомеоморфно. Как быть? Мы хотим применить что-то, что вот только что было. So we want to apply something we've just seen. Okay, let me take an x inside M. And let me take the relative homology M modulo M minus X. this manifold is complicated. This manifold may also be complicated. But let's use the excision property. I take this as X, this as A, and by the definition of a manifold, each point X has a neighborhood homeomorphic to Rn. No surprises there. This is just the locally Euclidean condition from the definition of a manifold.
So, what did we Rn?
Oh yes, yes. Thank you.
And also there, after the excision.
Okay, so I take a neighborhood which is homeomorphic to Rn, a neighborhood of U. A neighborhood, moreover, an open neighborhood. Well, let me take B to be the complement. The complement of an open set is closed. And this M minus X is open. So this condition, in our case, is automatic. Okay, let me. This condition is automatic. Why? Because B is closed and A is open.
So what is it? M minus a point, right? I mean the B.
B is M minus U, where U is homeomorphic to Rm. Okay, now does everyone agree with this equality? So we have by taking the relative homology, we get something much simpler. The relative homology, we get something much simpler than the manifold M or M minus X. Now, my next claim is this group is isomorphic to the homology of dm mod Sm minus 1. which is again by the 5 lemma. Does everyone understand how to deduce this isomorphism from the 5 lemma? And by using what we already know, even if we don't know that the homology, that the relative homology is the same as the reduced homology of the quotient space, we still can prove that this thing is isomorphic to Z in degree M and to 0 in degree different from M. Okay, does everyone agree with this? The relative homology of the disk mod the sphere is 0 in all degrees apart from M, and in degree M it's Z. Так, все ли поняли, что здесь произошло? Относительная гомология. Даже если мы не знаем, что относительная гомология вот этой штуки, это то же самое, что гомология фактора, приведенная. Если мы просто знаем гомологии вот этого, то мы уже можем вычислить относительные гомологии просто там из длинной точной последовательности. Okay, so we can do the same for n, and we get z in a different degree, which means m and n are not homeomorphic. Это вы доказали, что многообразие разных размерностей не могут быть гомеоморфны. Все ли поняли, что произошло? Okay. Does everyone agree with this? Yes, no? Sort of? Okay. Now, well, this is just one application which shows that relative homology and the excision property really is useful. In this example, the homology of the homology of M is complicated, the homology of M minus X is complicated, but the relative homology is easy. Okay. By the way, In the Meyer-Vitoris case, we have this condition. X is the union of the interiors of A and B. And as an exercise, prove that this condition is also important. Basically, if you take X, for example, to be any space and you partition it into an open subset and the complement of this open subset, then this will often not be the case. And as you can check by constructing an explicit example, the Meyer-Vitoris sequence is not exact. Okay. Well, this was a side remark. Let's see what we do next. Okay, let's try to prove let's try to prove something about relative homology. For example, I mentioned a few times that the relative homology of can often be seen as the reduced homology of the cohesion space. Well, let's see when this is possible. Here is a reasonably general condition. Suppose I have a space X and a closed subspace which has a neighborhood that deformation retracts onto A, onto the subspace. Then my claim is that the relative homology is the same as the reduced homology of the quotient space. This would help us. For example, here, the quotient space in this case is the M sphere, which is something very familiar. But anyway, let's try to see why this is true. Okay, are there any ideas? Suggestions? What to do if you don't know what to do? Well, it depends. But in topology, if you don't know what to do, draw some diagram. So let's draw some diagrams. Well, I have X. Okay, X contains A, but it also contains U, and U contains A. Okay, X by A. X by A, X by A is something, U by A is something, but A by A is a point. Does this diagram give anyone any ideas?
If we get something from that side, then we can use phi lemma. I mean, I'm planning to use phi lemma, but we need more. Two more sets for diagram.
Well, let's see. So we have this group, which is what we're interested in. And we have this this condition that U deformation retracts onto A. Okay, and what else do we have? A is assumed to be closed, and A is assumed to be closed. Yeah. A is assumed to be closed, so X minus A is open. So we have an open cover consisting of two elements, X minus A and U. We know from last time C U X the inclusion of CUX in C of X is a quasi-isomorphism. Okay, let's see. Does everyone remember what this is?
Excision.
Well, it's something we use to prove excision, but in itself, this is just the complex of simplices such that the image of each of those simplices is contained in either X minus A or U. То есть это такой подкомплекс, который, как Абелева группа, порожден симплексами, сингулярными симплексами, у которых образ лежит в одном из двух. Здесь множество. Okay. And we have the inclusion of this into the whole singular chain complex, and as I mentioned last time, this map is a quasi-isomorphism, and those who are interested in reading the proof is in the notes which are on the course web page. Значит, для тех, кому интересно доказательство, это нетривиальный совершенно факт, но верный тем не менее. Значит, доказательства есть в записках, которые выложены на сайте. Okay, well, let's see if this is any help. Let's see if this helps. So we have a quasi-isomorphism which is basically given by the inclusion. Now okay, let's think. Does anyone have any idea how to do this? So we want to prove that the map, the relative homology map, induced by the either X mod U or X mod A, induced by these is an isomorphism. And we also have this. And there is a trick which we used last time when we proved the excision property. Actually, maybe the excision property already suffices. Let's think a little. Так, ну будут какие-нибудь предложения? Вот, значит, вот нужно доказать, что вот, значит, отображение понятно какой изоморфизм. We need to think. Так, значит, да, будет ли какие-нибудь предложения? Если предложений не будет, давайте подумаем где-то минуты 3. Let's think for 3 minutes because I've forgotten how this works, and so we need to think. Are there any suggestions? Basically, all the ingredients are there. We only need to understand what is where.
Consider the regulatory sequence for COU.
Let's see. Well, the Myvitor sequence. Let's see if it helps.
Cover X with X.
Yes. Let's see. So we have X minus A and U, two open subsets, and they go to two open subsets of the space X X by A. Now, okay. Well, let's see if it works. Let's call this map P. What is P of X minus A? P of X minus A is an open subset of the quotient space, and this open subset in fact is homeomorphic to X minus A. P of U. P of U is simply U which is an open subset. That is a homotopy equivalent point. Then, well, the Maya-Vietoris sequence on the nose doesn't quite tell us what we're after, because we only have seen the absolute Maya-Vietoris sequence, which means the Maya-Vietoris sequence that we know only involves the absolute reduced and non-reduced homology groups. But let's let's use this remark. This remark may help. So we want to prove that P from C x U to C x by A U by A let me call this map F hash to distinguish it from, P hash to distinguish it from P. And we want to show that this map is a quasi-isomorphism. By the way, I've used this word a few times, but does everyone understand what this word means? A quasi-isomorphism. A quasi-isomorphism is a map, is a chain map of complexes which induces an isomorphism of the homology groups. Okay, so my claim is that C star of X mod U is actually isomorphic to C lower star of CU lower star of X mod C lower star of so mod C lower star of U. Really need to find the little thingy of U. Now, scrub that. Let's okay. I want to show that this complex is quasi-isomorphic to C over star of x minus a mod mod basically u minus a. Well, let's assume this for a minute. When we apply p to x minus a, nothing happens. The image of x minus a is homeomorphic to x minus a. The same happens with the same applies to u minus a. So if let's see if we can construct a quasi-isomorphism between these two complexes. And this is something which should be similar to what we saw last time when we proved the excision property. Sorry, U. Okay, here I have Cu of x. Well, let me take again Cu, the identity.
This is more easier.
Cu of x mod C lower star of u 0. Okay, so this is an isomorphism. This is a quasi-isomorphism. So this is also a quasi-isomorphism. So I have this complex here, and here I have something which resembles this complex, but let's see if it's exactly the same. So CU, C upper U, what is it? Well, it's the subcomplex of all singular complexes which are either inside entirely x minus a or are entirely inside U. And then we take out those which come from U. So my claim is that this complex is exactly the same as this one. And I have constructed a quasi-isomorphism as well. More precisely, it goes from this direction to this direction, from this group to this group, and similarly we have the same thing downstairs, and it works.
Of course, this is true because we need to assume that A is properly contained in U. In case that A and U are the same thing, say A is closed and open, we just exclude this possibility. And then to look at to see its quasi-isomorphism, you just look at the homology groups, which is exactly what we proved, that you exclude the closed subset at the same time. So previously, the pair XAB here is XUA, and for the second row that you just exclude one point, which is the point shrinking from A. That's the isomorphism, I think.
Okay, so two remarks. U is open, A is closed, but it may happen that U is exactly equal A.
Yeah.
This is allowed. In which case, A by A will still be a point. And even if A is empty, what's the empty set by the empty set? I think it's still a point. Anyway, so we have this map, and it is a quasi-isomorphism from this diagram. Now, this is an isomorphism, so this map is a quasi-isomorphism. And okay, we'll have a break in a minute. So the conclusion is that the homology map, the relative homology map X mod U and X by A mod U by A is an isomorphism. And then we use the fact that actually A by A is a point, and U by A, it's not a point, but it's homotype equivalent to a point. And why? Well, because U deformation retracts onto A. So we can construct a homotopy which deformation, using this, we construct a homotopy which deformation retracts u by a onto a point. Okay, well, I've run over time again, but then I arrived late. So let's have a break, 20 minutes, and then I will say a couple more things about this, and after that we'll move on. Smooth as it was supposed to be, but anyway, we proved the theorem we wanted to prove. Does everyone agree, disagree, or something in between? Значит, в общем, после каких-то там раздумий, мучений, значит, теорему все-таки доказали. Значит, согласны, не согласны, или согласны частично. Так, нужен какой-то ответ. А в чем была теорема? Вот кто-нибудь помнит? Да, значит, относительно гомологии. So the theorem was that the relative homology x mod A is isomorphic to the reduced homology of x with A collapsed. And this is true if A is a neighborhood deformation retract, meaning a closed subset such that there is a neighborhood which deformation retracts onto A. And maybe there is we don't need all of these assumptions here. All we need is there is a neighborhood U which is open, and such that the inclusion of A into U induces an isomorphism of the homology groups. But in practice, this is the condition which is automatic in many cases, such that as CW pairs and so on. And again, we argued as follows. We first said that instead of x comma a, we could consider u, x comma u. Why? Well, precisely because this is the way we chose u. And then we look at this diagram and see what are the induced maps. And well, this is the one we want to calculate, and we use these quasi isomorphisms which follow from the diagram. And once we have, once we arrive here, we basically use the fact that U by A is homotopy equivalent to the point. Why? Well, precisely because U deformation retracts onto A, and even if no, I think No, we really do need to have some kind of deformation retraction to conclude this. Anyway, so let's assume A is a neighborhood deformation retract. Then this is a point, and we get the homology mod a point, and it's the same as relative as reduced homology as we have already seen. Does this make sense?
Could you please repeat why there is a quasi-isomorphism between x quotient A, u quotient A to the B? So the second row on
this one?
This one.
Well, we basically repeat the same argument we have this quasi-isomorphism upstairs, and we have a similar one downstairs, for which follows by the same argument.
And the argument is like in the proof of extension theory.
Yes, the argument is very similar. Namely, we construct an open cover, and then we express the relative homology chain complex as something which only involves singular simplices from inside one open subset, mod the singular simplices from the intersection. So there's a map from this complex to this complex, and in fact in the other direction. This is not just a quasi-isomorphism; it's an isomorphism. Okay, does this make sense? Well, let's see some applications of homology theory. We've already seen a few, but let's see more. Well, there's a theorem which generalizes a theorem by Jordan on curves in the plane. The theorem by Jordan says that if you have a continuous non-self-intersecting embedding of the circle in the plane, the complement has precisely two components. And we will prove the same for Euclidean spaces of arbitrary dimension. And we will actually proceed in 2 steps. So step 1, suppose I have I dm Rn and embedding. Then the reduced homology of let me think a little whether let me think. Okay, let me replace this Euclidean space Rn by Sn Sn minus I of dm is 0. Okay, and the second part is well, the second part is very similar. So suppose we have I an embedding of the this time I take the M sphere instead of the M disk. And my claim is the reduced homology of Sn minus the image of the embedding is isomorphic to the reduced homology of Sn minus I Sm minus 1 and here I need to take plus. Okay, let me think. Is it plus 1 or minus 1? Okay. Well, let's take n equal 3. And m equal 1, then I have something in degree 1 on the left. On the other hand, m minus 1 is equal 0, and here I have something in degree 2. So I think it works. One plus 1 is 2. Okay. Well, let's prove this this theorem, and well, the second part follows formally from the first one, but to prove the first part, we need some kind of a continuity property for singular homology. Well, there are several ways to state this property. I will only explain a particular case which we need for this theorem. Well, suppose I have X, a space which is the union of an increasing sequence of open subsets. Then the homology of X is isomorphic to the direct limit of the homology of the UIs. Now, do we all understand what this limb with an arrow means?
Direct limit.
Yes, but do we all understand what a direct limit is? Okay, so let's well, let me briefly explain what it is, but really briefly. And there is a more detailed explanation in Hatch's book and in other books as well. So this thing is the direct limit. Okay, now the short explanation is the really short explanation is we have this U0, U1, etc., and all of them together they form a diagram, and we only need to consider the co-element of this diagram. Well, this explanation probably does not really explain anything. So let's which is why I used a different color to write this. But let's see a more explicit construction. Suppose A is a directed set. Now, what does this mean? It means that we have a relation less than or equal on this set. We impose two conditions. Yeah.
I think it's broken now.
Could you check if the microphone is working? I've just stepped on the microphone, and I'm not sure it's still working. 1, 2, 3. Testing. Okay, I'll just. It's working. Well, it's wonderful. Anyway, we have these two properties. Firstly, every element is less than or equal than itself, and secondly, there's another property if x less than or equal y less than or equal z, and this implies x less than or equal z. For all x, y, z in A. So this is very similar to a partial ordering, but not quite. With partial orders, we don't need this condition, but we have one extra condition, namely x less than or equal y, and y less than or equal x implies x is equal to y. We don't impose it here. By the way, can someone give me an example of a directed set which would not be which would not be partially ordered? Something from year 1. A На первом курсе есть такой курс, называется «Введение в дискретную математику и непрерывную математику». И вот там, значит, там что-то про это было.
Example of a directed set.
An example of a directed set which such that this relation would not be a partial order. Okay, well, it's an exercise, a question. Let's move on. Now, suppose we have Gi. Well, suppose we have a directed set. And suppose we have a family of abelian groups indexed by elements of A. And suppose we have a map Fij from Gi to Gj for all ij in A such that I less than j. And these maps are homomorphism of abelian groups. And we require that if I is less than j and j is less than k, then we have a map Fij, and we also have a map Fjk, and we require that the composite map should be Fik. In other words, if we consider A as a category with just one arrow between every two non-identical objects, then this data is just a functor from this category to abelian groups. And I, by the way, I less than j simply means I less than or equal j, but not equal. Okay, now we can define the direct limit as follows. First of all, we take the direct sum of all the groups, And this direct sum may well be infinite. And then inside this direct sum we take the subgroup generated by all differences, x minus Fij of x, where I and j are arbitrary elements of A such that I is less than j. And x is an arbitrary element of, with the way, of Gi. Now we will need two things about direct limits, and these things are. Two useful facts about direct limits. Let me make it three useful facts about direct limits. Fact number one. Suppose I have x inside Gi, where I and the Gi are as in the previous construction. If x goes to 0 in the direct limit, then, so this is fact number one. Then there is a j greater than I, such that Fij of x is 0. So this is fact number one. Fact number two, for every x inside the direct limit, there exists a y inside, there exists an I inside A and a y inside Gi, such that y goes to x. Basically, in both cases, I'm using maps from each individual Gi to the direct limit, which are manifest in this construction. So fact number one, fact number two, fact number three. The direct limit on abelian groups is exact. And which means it takes exact sequences of of exact sequences of functors to exact sequences of functors. Anyway, I encourage everyone to read something about direct limits, whether in Hatcher's book or elsewhere. Probably Hatcher's book is best because, it contains just the bare basics, and this is all we need. Can someone give me an example of a non-trivial direct limit? Well, non-trivial meaning not all maps are identical. If all maps are identical, are the identical maps, then the direct limit is just the group itself.
That's usually commutative algebra.
Yes, for example, localization in commutative algebra. Does any of these words make any sense whatsoever? Well, let's consider a particular case of localization. Okay, I'll erase this. Let's represent Q as a direct limit of z's. So, example. This example is really quite straightforward, but let's try to understand it. Well, let's take all cyclic subgroups of Q. A cyclic subgroup is a subgroup generated by one element. And basically, to each cyclic subgroup, we associate itself. The same group. The order the ordering is given by inclusion. One subgroup is less than another subgroup if and only if it's contained in the other subgroup. If I have two subgroups and there is a third one which contains both of those, which is basically an exercise in very, very simple number theory. So we are allowed to consider the direct limit, and well, it's pretty straightforward to show that the direct limit is Q itself.
I'm confused. Sorry. do you mean by cyclic subgroups?
Well, a cyclic subgroup is a subgroup generated by one element. If, for example, I take q squared instead of q, then this wouldn't work. It's not true that for every two cyclic subgroups there is another cyclic subgroup that contains both of those. But for Q, it does work. Okay, well, it's just one example, and as Wei says, a more general example is localization with respect to a multiplicative subset. And well, let's basically let's just mention this without any more details, because we're short on time. Anyhow, okay, so I do encourage everyone to read something about direct limits. Значит, там в Хатчере написано про прямые пределы, значит, пожалуйста, прочтите. Okay, now once one is familiar with the definition, this continuity property is completely straightforward. The main observation is, suppose I have a compact subset of X by the definition of a compact subset. So the main idea why this works is that every compact subset is included in some UI. Well, because UI are included in one another, and they form a cover, and there's a finite subcover, and basically, since they're all included in one another, a finite subcover would be just one particular UI. Does this make sense? Там, конечное подпокрытие, оно в данном случае будет состоять просто из одного множества. Почему? Потому что они все друг другу вложены. So, using this and the definition of singular simplices, it's straightforward to prove that we have this. And but let's see, we have this on the level of co-chain complexes. But to pass to homology, we need to know that lim is exact, the direct limit. There's also the inverse limit, which is not exact. But the direct limit is exact. Okay. Так, значит, понятно ли более или менее, что мы здесь хотим? Okay, well, let's prove at least one part of the theorem. Let's prove part 1. Well, let's see. Let's see.
Можно вопрос? Вот, то есть этот изоморфизм, он есть не просто для произвольной теории, не для сингулярной?
Ну, не только для сингулярной, но нам нужно какое-то условие вот, типа непрерывности, которое имеет место для сингулярной, но, наверное, можно придумать такую теорию, которая в этом смысле не будет непрерывной. Вот, а может и нет. В общем, здесь нужно чуть подумать. Следует ли, следует ли из аксиом вот эта вот версия непрерывности, или ее нужно требовать в качестве отдельной аксиомы. Okay. Well, let me think. Yes. So part number one. Part one. We need to understand the homology of reduced homology of Sn minus I of dm. Well, let's induct on M. Well, for M equals 0, there's no problem. And yes, what do we want to prove? Want to prove that this group is 0. Let's see what happens when we pass from M to M plus 1. I want to replace dm and dm plus 1 with I m plus 1. In other words, the product of m plus 1 copies of 0, 1. Let's see. So now I do what? I take I m plus 1 and represent it as I m plus 1 plus union I m plus 1 minus, where the plus and minus correspond to the last coordinate being from 0 to 1/2 and from 1/2 to 1. And then I apply the Major-Vittorius to the following thing: Sn minus I of I plus Sn minus I minus. And by the way, the union of these two will be the complement of the intersection. The union of the complements is the complement of the intersection. So instead of Sn, I here have I of I. So these are m plus 1 dimensional. And what's the intersection of these two? The intersection is I to the mth. Does everyone agree?
Could you repeat this?
These are two m plus 1 dimensional cubes. Mm-hmm. The intersection is an m dimensional cube, mm-hmm. Which I denote as I to the mth.
To be precise, we shall we to apply MV sequence test, we need open subsets of I plus 1. So
well, the unit cube is compact, so the image is also compact, and the sphere is Hausdorff, so is closed. And so when we take the complement, we get something open.
Okay. Yes.
So yes, indeed we need open subsets, but in this case this is automatic. So we apply the Maya-Vittori sequence, and what do we get? We get an isomorphism between okay, so the intersection is the intersection of these two is the complement of the union, so it's n minus I of I m plus 1. And this goes to HI is n minus I m plus 1 plus the sum of plus HI. No, too many i's. Let's put a k here. Otherwise there's too many i's. I plus 1 minus. Okay, now I have these isomorphisms from the Maya-Vittori sequence. Does everyone agree? Oh, by the way, I need to put tilde Need to put the tilde everywhere. Why do we have an isomorphism? Because on the left and on the right we have the reduced homology of the union. And the union is the complement of the intersection. And the intersection is a lower dimensional cube, and for the lower dimensional cube we can use the induction hypothesis. Okay. Okay, so we have an isomorphism from the.
Why is isomorphism?
Well, because in the Maya-Vitoris sequence on the left and on the right we have the reduced homology of Sn minus I of a lower dimensional cube. And by induction we know that for the lower dimensional cube we have this equality. Значит, индукция по размеру куба, то есть по размерности куба. Для нульмерного куба все окей, предполагаем, что для m-мерного все окей, движемся к m плюс одномерному. Вот, значит, что будет, если мы пересечем? В смысле, не, наоборот. Что будет, если мы возьмем объединение вот этого с вот этим? Получится дополнение к пересечению. А что такое пересечение? Пересечение – это образ меньшего куба. Okay, so if one of these groups is non-zero, then then the map into either the plus version or the minus version is non-zero. Okay, it's too long. So if this group is non-zero and this is an isomorphism, then the map to the first summoned or to the second summoned is non-zero. One of the maps is non-zero. Okay, and so on. After we find one non-zero map, we apply the same procedure by subdividing further either the plus version or the minus version. As a consequence, we get a sequence of a sequence of n plus 1 dimensional cubes such that the intersection is an m-dimensional cube, and HK Sn minus I of Im to HK Sm minus I okay, I'll write it again because this is hard to read. So the map is non-zero for all I. Or non-zero for all J. And this is basically it, meaning this is basically the contradiction. But let's understand why. The direct limit commutes with taking homology. This is what continuity means. We've just seen it. Now the intersection is a lower dimensional cube, so the homology of Sn minus I of Im is 0. And this is and this is the limit, the direct limit of the groups of these groups. Now, if we have an element, and now we use the properties which the useful properties of the direct limits. I have this group, which maps into each of these groups, and it also maps into the direct limit. if okay, so if I have an element in this group which is non-zero, then it maps to zero. It maps to zero here, and why? Well, this is by the induction hypothesis. So it maps. It goes to zero at some finite stage.
Извините, я не понимаю, что и зачем происходит. У нас была последовательность вложенных n плюс 1 мерных кубов.
Правильно. Да, значит,
Пересечение это.
да, значит, вложено так, что пересечение n-мерный куб. Значит, дальше мы,
Вложили и пересечение получили n.
ну, потому что мы строим каждый следующий куб, значит, деля пополам ребро предыдущего куба.
Can we say that the non-zero maps are injective than we are not because it comes from asymptote?
Well, yes. Well, in this case, we can claim that anyway. Let me just think a little, and then we'll finish it. Probably we need something more than just a map being non-zero. But let me think what exactly it is. So we. Well, these groups are all isomorphic. Let's think. Basically, again, we have all ingredients. We just need to understand which one goes where. Okay. Well, here is what I missed. We start with an element of an element x in some so we want to prove that okay, let me just say this, and then we'll finish, because I think nobody is following anymore. But just in case, let's say it for the public on the other end of the screen. So what happens? We start. We take an x in some hk of Sn minus I n plus 1. Let's suppose there is a k, there is an x which is non-zero. Okay, now
and it must map to one component.
yes, so x is non-zero, x goes to non-zero to a non-zero element in one of these components. Either this one or this one. And k is the same one as the one we chose from the start. Okay, and then we do the same thing we just did, namely we construct a sequence of subcubes, which such that the intersection is a cube of a lower dimension. In the direct limit, x must go to 0. So x goes to 0. In some of the groups that would take the limit of. And which is a contradiction, because this is at each step we choose the next cube in such a way that x goes to non-zero, in the corresponding group. Okay, I think I don't even want to count the amount of time that I've run over. So basically we need to finish as soon as possible, but before we do, are there any questions? Questions, comments, criticism, well, except the obvious fact that I have run out of time. Okay, well, then this is it, and I repeat, no class next week.